Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So we are still at this topic on multivariable calculus. So basically now we're gonna discuss this concept of maxima and minima when we are dealing with multivariable calculus, a function with basically two independent variables. Now this is not something new. We have basically done this before when we discuss derivative. It's just that previously we only deal with a function that have only one independent variable. Now, what if we want to find the maxima or minima when we are given a function that contains more than one independent variable? So in the for this course, basically we're going to look at a function with two independent variables. So we're going to basically apply the same concept, how to basically find the maxima or minima. So let me just get the slides. Okay, so maxima and minima. Okay, so now you please make sure that you have already familiarized yourself with the concept of partial derivative, because we're going to use partial derivative a lot, okay, because we cannot run away since our function now consists of two independent variables. So we're going to see how we want to locate the local maxima or minima for the functions of the type z equals f of x and y, where we have two independent variables. So we're going to simply extend. So it is a simple extension of the second derivative test from function of a single variable to functions of multiple variables. We're going to assume that all second order partial derivative exist for the function f, for this function, in some circular region of the xy plane. So that this guarantees that the surface of z, okay, equals f of xy, the surface of our output or dependent variable has no sharp points, breaks, or ruptures. In other words, it's going to be a very smooth like this. I mean, if we have this kind of shape, 3D, so we can locate the local, this is a local maxima, right? I mean, if you understand the concept clearly, this is the highest point compared to all the other points, all the other coordinates. Okay, this is the highest point. For this one, no, because that's why we're going to basically rule out any function where the second order partial derivatives are not in existence. So we're going to avoid this and this, as well as this one, no sharp point. So we're going to simply going to be dealing with smooth surfaces, okay, smooth surfaces with no edges, no sharp points, and no breaks. Okay, so how do we find this? So this is how we define local maximum or minimum of a surface technically. So if we are given a coordinate of A and B, if x equals A and y equals B, now f, the output z, remember z of this would be a local maximum, the highest point on the surface if there exists a circular region, because now we are dealing with 3D, so it is a circular region. Okay, remember your cup, okay, your coffee or tea cup. Okay, so circular region in the domain of f with A, B as the center. So A and B has to be the center, and it has to be the highest, greater than or equal to all other values of x and y in the region. Okay, so it has to be the highest or equal. Okay, the opposite is true for local minimum. If we have a circular region in the domain of f, okay, A and B, such that the output f of A and B would be the lowest, okay, smaller than or equal to all other values of x and y. Now, to visualize this, so figure A, this one illustrate local maximum, where if you look here, the value of A and B, okay, A and B and 0 here, okay, A and B, at this point, okay, is the highest compared to all other points on the surface. B here illustrates a local minimum, where the output f, A, and B is the lowest compared to all other values of x and y. Okay, all other values of x and y. While C illustrates a saddle point, where if you look from the the x point of view, this is a local minimum, while if you look from the y point of view, this is a local maximum. Okay, local maximum. Okay, so let's then see how we can apply this partial derivative. Okay, partial derivative. So the partial derivative f sub x and f sub y at a local minimum or local maximum. Okay, when partial derivative of f exists, okay, so these two exist, okay, in a circular region surrounding a, b are equal to 0. If the partial derivative of f exists, so the partial derivative of the function f sub x and f sub y at either local minimum or local maximum, they are equal to 0. Why? Because they represent the slope of the tangent line. The slope of the tangent line. So when we have either a local maximum or local minimum, like in that 3D, okay, in the previous picture here, okay, so this is the slope of the tangent line, right? F sub x as well as f sub y both must be 0 because you're going to have a horizontal tangent line regardless from whichever perspective that we are looking at this bowl, this cup, either from x point of view or from y point of view, the slope of the tangent line is 0. So that's why we come up with this definition, f sub x and f sub y at local minimum and local maximum, they are equal to 0, because when we look from both point of view, they are equal to 0. They are horizontal. The tangent lines are horizontal. Okay, so this gives us to theorem 1. Okay, theorem 1, this is something that you really need to understand and memorize. Okay, you don't have to memorize actually, but once you understand it, you can simply apply it. Okay, so this f, okay, at this point A and B, the output will be a local extremum. So if this is a local extremum, okay, and if f sub x and f sub y both exist, then basically the slope, okay, of the tangent line, okay, tangent line. So because now we have two tangent lines from x point of view and from y point of view, at this local extremum must be 0. Okay, must be 0. However, the opposite is not true. So this has to be a local extremum first, and then, only then, this would be 0. But if, let's say, we know, let's say we start with this statement, so this has to be the first statement, then this is the second statement. But we cannot start with this. The converse of these theorems is false. If we know f sub x and f sub y are zeros, the point AB may or may not be a local extremum. For example, it can be a saddle point. When it is a saddle point, it is not a local extremum. Okay, it is not a local extremum. Okay, so we need to find all points. So if we are asked to find this local maximum or local minimum, the first thing that we need to do is to locate or the point AB such that the slope of the tangent lines are 0. And then we need to test. We need to test whether these points are they local maximum or local minimum, or is it a saddle point. Okay, so there are two steps. So first we need to find all the points, and then we need to test the nature of the point, okay, and nature of all these points. So this would then basically, so point AB, all the points where the partial derivative, the slope of the tangent lines are 0, these are called critical points. They are called critical points. And since we don't know, because we need to do a second step here, we need to test, right? So first we need to, number one, we need to locate, right? Number one. And number two, we need to test. After we have located all the critical points, we need to test whether the critical points are their local maximum or local minimum or saddle point. And because of that, we need to apply the second theorem, where we're going to use the second derivative test for the local extrema. Okay, so let's say if we have this function, okay, our function consists of two independent variables, x and y. And let's say f sub x and f sub y, they exist and they're equal to 0. We managed to locate A and B, which is a critical point. Then we need to do the test. All second order partial derivative of f exists in some circular region containing AB as center. Okay, so this basically we need to have the f(x(x), f sub y(y), and f sub xy must exist. Okay, it must exist. Then, okay, so let's say we call this f sub xx as A, f sub xy as B, and f sub yy as C. So we have 4 cases. Now, first, okay, we have to basically take the product of f sub xx and f sub yy, and then subtract it with b square, this the cross partial derivative. This is the own partial derivative, own second derivative, own second derivative, the cross partial derivative. Okay, so A multiplied by C, subtract B square, must be positive. If it is positive, and then A, this A is negative, okay, then this is a local maximum. Okay, frowning face. Case number 2, where AC minus B square is still positive, and A is positive. So we have a local minimum. Case 3, if AC minus B square is negative, then F has a saddle point at AB. It is a saddle point. It is both maximum and minimum, but we cannot decide which one. Okay, so that's why it becomes a saddle point. And case number 4, if AC minus B square equals 0, the test fails. Okay, the test fails. If you want to know more of the reasons behind this, then you have to take higher levels of mathematics. I mean, at the moment, you only need to know these 4 cases as given. Okay, as given. Of course, there are explanations, there are justification as to why we focus on this A and C, we multiply this, and then we subtract B square, but that will be outside the coverage of this course. Okay, so let's have this, let's try to do this example. So find the local extremum. Okay, find the local extremum of this function x square plus y square plus 2. Okay, so now the solution. So this is how, if we were to draw the graph, it will be this cup. Okay, it is cup. There is a local minimum. Okay, at this point. Okay, at this point. Okay, where z equals 2. When both x and y equals 0, z equals 2. Okay, so it is 0. So let's try to do the step. So step number 1, we need to find the critical point. So how do we find the critical points? So the critical points, we need to basically find such that f of x, okay, and equals 0, and f of y equals 0. So how do we do that? So here, so what is our f of x? It is 2x. And what is our f of sub y? It is 2y. And equals 0. So if we make this equal to 0, then we have basically, if we set this to equal to 0, x equals 0. If we set this to equal to 0, then our y equals 0. So in this case, we have a critical point 0 and 0 is a critical point. And there is only one critical point. Okay, one critical point. Okay, so that's step number 1. Okay, so we have only one critical point here. Step number 2. Okay, so step number 2, it was we need to find the second order partial derivative, right? Second order partial derivative. So we need to, so step number 2 here. Step 2, we need to find fxx, fxy, and fyy. Then evaluate at x equals 0, y equals 0, the critical point. Okay, so fx previously was given as 2x, so fxx equals 2, fyy equals 2y, fy equals 2y, fyy sub yy equals 2, and f sub xy, there is no y here, equals 0. And from previous example, this would be A, this would be C, and this would be B. So we need to check which cases. From out of the 4 cases, we need to evaluate AC minus B square. So our A is 2. 2 multiplied by 2. So 2 minus, this is 0 square, equals 4. 4 is greater than 0. So we have ruled out case number 3 and 4. So we have, right, case 1, 2, 3, 4. So we have ruled out 3 and 4. So either 1 or 2. So to know which case, we need to evaluate this. Okay, so since f sub xx, okay, I mean, regardless, even when we substitute 0 here, there is no x here, so this becomes 2. It is positive, so positive means we have a local minimum. Okay, so 0.00 is a local minimum. Okay, simple as that, right? So this is basically what so step number 3. I mean, we have done step number 3 here, so I hope it should be simple enough. Okay, so we have case 2 basically, because this is positive. Okay, right, positive, we have a local minimum. Okay, this example, I'm gonna leave this to you. Oh, again, don't forget the 3 steps. First, you need to find locate the critical points. Remember, there might be more than one critical points. How do we do this? You simply find, okay. Step number 2, you need to find the second order partial derivative. Okay, fxx, fyy, fxy. And then step number 3, you need to evaluate basically fxx multiplied with fyy minus fxy square, right? And then evaluate, okay, greater than or equal to 0, and then check fxx, and then you decide, is it a local max or local minimum? Okay, and even from here, you need to also decide whether it is a saddle point or whether the test failed. As simple as 1, 2, 3. Step 1, 2, and 3. Okay, so I'm going to leave this example to you.